Okay, so last week we covered chapter 3A, which is the first part of the design process and the role of CAD in it. Okay, so today we are going to move on to chapter 3B. So chapter 3A covered, all right, the entire design, the types of design. We had 5 types of design, all right, and then it described the closed loop product cycle, okay, and then the difference between product cycle in a conventional manufacturing, computerized manufacturing, and then we went into the depth of what is design, the morphology of design, leading to the 7 phases of design, all right, in which, okay, we covered each phases of the design, and in extensively we covered the first 3 phase, all right, the conceptual design, embodiment design, and detailed design, okay, and we discussed all the specific tools which are used to evaluate, all right, the phases of this design, especially the first phase, which is the conceptual design phase. Okay. Okay, now, and then we moved on into discussing, all right, the principles of design for manufacturing and assembly. Okay. And then the principles of design for manufacturing. Okay, and then we looked at other design considerations and we stopped at that. Okay, now we are at the 3B section of this chapter. Okay, so let me get my pointer out. Okay, so the 3B section, all right, it discusses the computer application, the computer application. So there are 3 major computer applications in the engineering environment. Okay, so we have all right, the design portion, the analysis, and the manufacturing. Okay, so the design involves coming up with the entire design concept, manufacturing, making the product realizable, and before we manufacture, all our design concept has to be analyzed. All right, now moving on to computer application in design. All right, so this is hang on. All right, so we hear is anyone, just a minute, just a minute, just a minute. Is anyone sharing the screen or meddling with the pointer?
No.
Okay,
No.
because I seem to be getting interference. Okay, let me try again. Okay, so the conceptual is under the application of computers in design stage. Okay, just now early on we had the analysis stage, the manufacturing stage, and the design stage. All right, so if you look at the design stage, all right, we have the conceptual and also geometrical modeling design stage. All right, so in the design stage, all right, both this conceptual I cannot, okay, hang on. Okay. All right, both the conceptual and the geometric modeling, all right, uses a lot of computer application, okay? So over here, we need the use of hardware as well as the software. For some reason, I don't know what is wrong with my presentation. Hang on. Okay, sharing my slide is creating problems. Okay, never mind. I won't use the pointer for a while. Let's see. Okay, so both the hardware and the software, right, is applied under this design. Okay, so we have the visualizing and the styling, all right, of products for concept generation. Okay, whereby you know what concept generation is, the creation of the idea of the product, all right, the birth of the product and everything. And then CAD tools are widely used in graphics and 3D modeling. So naturally, the entire concept is translated into the embodiment of the model through the CAD tools. So this is the software. And then when we go into the hardware, all right, so we have tools like 3D scanner, digitizer, pointing device, etc., okay, which helps us manipulate, right, and operate this CAD tools, okay. So under the application in design, we are to be aware, all right, we are to be aware that we have many softwares, all right, application simply means softwares, which are present in the market to assist us in performing the computer-aided design, all right, building of the geometry. So some examples given over here would be like AutoCAD, Pro Engineer, SolidWorks, you're using CATIA, Solid Edge, and many others, okay? And then computer application in analysis, all right? So basically this involves the engineering analysis and optimization of the design stage, okay, using the computer application, whereby as discussed previously, all right, what are the types of analysis we can do, right, on our model or product, analysis like structure analysis, strength analysis, heat transfer, static, vibration, all right, so many. So analysis may be used as a source of design verification for the design calculations and predictions. So this analysis, basically they are done based on the formulation of each of these topics, okay? And based on the formulation, we want to study the current scenario and we can predict the future behavior of the product, okay? So this involves CAE tools like FEA, CFD, ergonomics, etc., okay? Examples of softwares directly in analysis would be like Abacus, ANSYS, and in CATIA, we have our CATIA analysis portion. So certain softwares are specifically catered for analysis purpose, where their design aspect is not so strong, okay? So softwares like ANSYS, where I recently went for a training, all right, their design module is also being built up very well. So when those days we had to actually import a lot of, 3D models from 3D modeling packages. Now ANSYS itself can actually build good 3D models. And then in the manufacturing environment, basically we use the applications to plan, monitor, control, and execute the manufacturing process like we have discussed before, all right? So basically the CAM tools are used to analyze. So when we talk about CAM tools, the software itself is used to analyze your manufacturing processes, be it casting, injection molding, all right, metal press forming, whatever, okay? And then, okay, it is also used to actually operate the CNC machines, whereby we can actually generate the codes directly in the software and channel them to the machine, okay? So this involves wide areas from process planning to marketing. So an example of a software is like Mastercam, we have Mold Flow, we have CAD Mold, we have SolidWorks Plastics. In CATIA itself, we have CATIA Lathe, CATIA Milling, like that many, okay? Okay, now we come to the digital mockup unit. So what is a digital mockup unit, or DMU? So it is a concept that allows the description of a product in 3D, usually in 3D, okay? So it comprises of 3D models which are positioned in 3D space to represent the form of the product to be developed. The objective is to have an important knowledge of the future or the supported product to replace any physical prototypes, okay? Basically, if you don't want physical prototypes, then we want to actually replace them with virtual ones, all right? So basically the role, I think my internet is an issue or what, I'm not sure. All right. So the role, okay, for this 3D modeling, it allows full visualization of complete product in 3 dimension, permits collaborative engineering, Okay, hang on. Okay, permits collaborative engineering as all users can see other people's work as it evolves. So this is what we term as concurrent engineering, what we went through in our first chapter. It improves error detection by locating clashes, interference in the early process. So basically, what digital mockup unit does is when we have a unit of product, okay, which is made up of multiple assemblies, and this particular product has has joints, all right, which has kinematic movements. So we can simulate the movements or the function of the product, okay, through this DMU. So DMU is actually a module which is also inserted in CATIA. So the goal basically to reduce time to market by identifying potential issues in the early stage of the design, and hence this will lead to the development cost being minimized because we can detect the errors, and we do not need to build physical prototypes because we can see the function of the product itself virtually, all right? And it increases the quality of the product, okay, by allowing greater number of design alternatives, okay? So we can look at what if scenarios. So this is an embedded video. All right, wait. Let me escape. I think I forgot to, in my presentation, include sound. So let me just quickly unshare and reshare. Okay.
Hi, this is Mohammed Shakil here, and you're watching an engine being designed in the Power Design Workbench.
Can you all hear the sound?
Yes, doctor.
Yes,
Yes,
yes.
yes,
It's
yes.
All
a
right.
little bit of combination of generator shape design, and it's being brought to the DMU Kinematics Workbench for a simulation. So basically, I'll show you how the simulation works. So reduce
So
volume.
just to give you some pointers, this is not covered in our syllabus, but if you wish to, you may look at tutorials. I have actually just added one tutorial in the UFuture. A link has been added on it for simple kinematic simulation, whereby there is a cube and a long shaft, okay, not shaft, a long rod, okay, and a DMU simulation was actually made through that video, okay. So you can refer to it in case you want to incorporate it into your mini project.
Hi, this is
So
Mohammed
basically, I'm
Shakil.
going to
So
forward this. You can look through it
reduce
your own time.
velocity,
I'm not going to show the
and
process of how it's going to be done, but
here
basically, this
is
is to indicate this is
you know,
how a
as you
DMU
can see in
kinematic
the
video would
four-stroke
look
petrol
like.
engine, you can
Sorry, a
see
simulation
the
would look like.
piston
So
moves
you're able
to
to
and
see the
fro
entire
when
rotation
you
of the
know the
product, the movement up
exhaustion
and
and
down,
combustion
okay,
strokes.
and whether there is
So what
clash, there's
happens here is
interference,
the linear motion
okay. So
over
this is the
here is
purpose
being
of
converted to the
DMU,
basically in the
okay. So you can view this video, right, in your own time. All right. The next portion of it, we are moving on into CAPP, Computer Aided Process Planning. Okay. So what is CAPP? Basically, we are looking at, we've seen this term, all right, in chapter 1. So it's process planning, all right, which begins with an examination of an engineering part. So now we are talking about the entire product or part moving into the production plant already. Okay, design stages over. So this is dealing with the manufacturing stage, all right? So the process planning begins with examination of an engineering part drawing, okay? And ends with the manufacturing process plans and instructions before we embark on the production. So this is an act of preparing processing documentation for the manufacturing of a piece, part, or assembly, okay? So basically in this process planning, we have two levels, the high and low level. So the high level is the general planning, identifying, grouping, order. So if you remember the chart on conventional planning, all right? So acquiring the raw material, the planning of the production personnel, the utilities and everything. So it's done by higher people in the organization. So either the manager, the supervisor, all right? And all. Now, when it comes to the low-level planning, this is detailing the general plan above, okay? So when we talk about detailing the general plan above, so let's just say it's an injection molding process or a casting process, then the technicians, all right, involved in the particular machining will actually detail the process sheets of what is going to happen one after another. So they are going to do the detailing based on the higher level planning, okay? So it's a two-way feeding, okay, which will finally form the entire route sheets. So process planners, what they do is they follow a consistent set of steps to develop process plans, okay, which involves primarily stock preparation, plan generation, and specifying the manufacturing parameters. So in general, the process planning is performed manually, okay, by highly experienced planners. So those who already know what to do one after another. So if you just send them a part, in their head, they already have the steps of the process plan, okay? So unless we are in the production plant, these things will not be something which is standard in our thought process, okay? And they possess in-depth knowledge of the manufacturing process involved and the capabilities of the shop floor facility, so the production floor facility. So when you want to first develop a new process plan, imagine now you get a new machinery and you're going to do your first injection molding. So you have to actually get a full process plan developed. So when that is going to happen, this is highly subjective because we are testing the machine out, labor intensive because we are learning it, time consuming, tedious, all right? And, you know, it can be pretty tiresome and boring when you're fully developing a new plan, okay? So the CAP, computer aided process planning, is the means to automatically develop the process plan from a geometric image of a component. So where does CAP come into play is basically it integrates the CAD and the CAM. So you have your geometric model. From your geometric model, we are going to analyze the manufacturing process. We are going to analyze the product structures through CAE. We're going to generate the NC codes, and then we're going to channel the NC codes into the machine directly, of course, assuming the machine is able to take in the channeling, and then we're going to manufacture the product. So if you notice over here, it is not labor intensive. Very little labor is needed, and it's more of an automated process. Due to the fact that there is an integration between CAD, CAE, and CAM, okay, in this case, we are just talking about CAD and CAM, all right? The entire document sheets, they are not exactly manual, so it's a full computer process and it will be documented one after another. So CAP takes the CAD data to production data and feeds it into the production system. Okay, just a minute. All right. So now the key development of such a CAP system, okay, is naturally when we're talking about CAP because it's computerized, right, would be the part design. We need to have a virtual CAD model. Next, you need the manufacturing facilities, like I mentioned earlier. You need the machineries, all right, and of course the setup of the entire production plant. And next, you need the capabilities. That means, number one, you need the machine to function to be able to support CAD, meaning it's able to input or import part design data and details, okay, into the machine to run an automated manufacturing, okay. Next, you need your personnel capabilities. That means your operators and everything should also be capable of actually, dealing with any troubleshooting problems that may arise, okay. So they are part design, manufacturing facilities, and the capabilities. So the basic steps of process planning, all right, we analyze part requirements, you select the raw piece, you determine what kind of manufacturing operation and the sequence. Then, of course, the machine tools, if it's, drilling, what type of drill tool and everything, all right? And the jigs and the fixtures and whatever equipment whatever inspection equipments, all right? Determine the condition of the machine, okay? And then the manufacturing time setup. So this particular slide here will give you an idea of what the process sheets will look like, okay? Now, what is the benefit of the CAP? It reduces process planning effort. Why? Because it's directly linked from CAD to CAM, and it's an automated system. So it systematically produces accurate and consistent process plans because it will naturally move you from one plan to another. When something is computerized, it is rare that you have an in-between gap of you forgot something, because when you have to, let's say, feed data into the machine, it will prompt you to have the data in full. Otherwise, it will not move. The machine may not start. All right. And once the machine is start, because it's a programmable thing, so one after another, there will be a sequence of steps, which is setup. So of course, it saves direct labor. And why material? With less error, less scrap. Okay, so material will be saved, no scrap. Tools can be guarded, all right, because we understand the nature when we are actually simulating in CAM. Where is the tool wear out? Where is the part wear out? Okay, so we talk about reducing the work in progress. So work in progress means once you've manufactured, there will be, the quality inspection, the scrap dealing, and all this different progressive work once your part comes out will be reduced. And then you reduce the process planning lead time. Okay, so lead time is the production time. Okay, as I said, because it's automated, so it goes in one after another, and all this will lead to a consistent process plan. Okay, which will automatically stop you from making mistakes. So now we have the CAP model. I really hope this pointer works now. Okay, let's try. Okay, so here is what we call a CAP model, okay, whereby you have your CAD system, which is then sent to your preprocessor. So in your CAD system, you preprocess, you assign material to your product, okay, you analyze it and everything, okay, and then you bring it into the CAP model, okay. So in the input, under your CAP model, you have your input and you have your output, okay. So the CAP model, how it functions is it draws in info from the knowledge as well as planning rules, okay. So what these knowledge and planning rules are, we'll see in the next slide. And after the output, you get your post processor, okay, to understand what are all the entire processes, and then you embark on your production. So this is the architecture where you have your CAD system, the preprocessor like just now, okay? And then we are looking at knowledge and planning rules. So this is the knowledge and planning rules, okay? So you have your machining module, all right? This is based on machining knowledge base. So what type of module you want to select, okay, depending on the manual of the machine itself, all right? And then you have your constraint application module and your process plan generation module. Your constraint application module has a sub root over here, okay, where you need to create your constraint. And how do you create your constraint? This is based on manufacturing knowledge base. So let's say it's an injection molding process, okay. Then there is a constraint of the type of plastic material that you need to use for the specific type of machining. So now let's say we are embarking into what we call this trying to inject plastic inject mold recyclable plastic waste materials, okay. So now this recyclable plastic materials, okay, they could be a mixture of composition, not necessarily PP, all right, or ABS, all right. It may not be polypropylene, it may not be specifically ABS, maybe a combination of all, including contaminants, maybe, because we are recycling and crushing the entire plastic, right? So when we want to machine this, sometimes we notice when you want to inject using either ABS or PP material, the entire injection speed is not enough. The injection temperature is the melting temperature is not enough. So all these things need to be understood based on your constraint creation. And where you will get this, you'll get this from your manufacturing knowledge. So your manufacturing knowledge, you need to have the knowledge of the material itself, okay? And you should be able to check, the rheology, meter level, and many other things. So these are all what we call the constraint. So with the constraint and the machining, you get your process plan generated. So there are two approaches to CAPP, which is the variant and the generative approach. Okay. So and the third approach is a hybrid approach, which is basically a combination of both. All right. So when it comes to the variant approach, okay, This is also what we call a retrieval approach. It uses a group technology code to select generic process plans from the existing master process plans, all right, or what we call baseline plans developed from each part family. And this plan, when it's extracted, okay, it's edited to suit the requirement of the new part. So what they're trying to say here is about 90% of the baseline plan is ready. The planners or the executors only need to modify 10%. So this is usually administered with a group technology coding system. So the parts are segmented into groups based on the similarity of the type of machining. So if you have a certain type of drilling, then they are grouped together. If it's a certain type of milling, then they are grouped together like that. Okay. So the challenge is in initially developing the first GT classification. So a new process plan must be developed manually and entered into the system database to create what we call the new baseline. So the whole idea here is when you get the first machinery and you're embarking on your first production, so you get your entire first set of rules and setup plans. So that will be like what we call the first base plan. Okay. So this is impractical in situations where small batches of widely varying parts are produced, where the manufacturing of those parts have different aspects or angles or variations. So then it becomes difficult because we have to alter a lot. So the disadvantage, all right, quality of the process plan depends on the knowledge and background of the planner. So there's a possibility that mistakes can happen based on the previous plan. Advantage, good in investment where the hardware and software required for CAP system is not high, okay, because it deals in more of a conventional based approach. Shorter development time and lower manpower to produce the process plan once we are already in the flow. Implementing a variant CAP system is straightforward since it only uses the existing plans, all right, which are there. And usually we get the existing plans from the catalog, okay. So this is the aspect of, group technology coding. So it's a part coding system which consists, it's a part of a coding system which consists of sequence of symbols that identify the part's design or manufacturing attributes. So the symbols are usually alphanumeric, all right, although most systems use only numbers, okay. So I'm only introducing the chain type structure, although there are 3 types of basic coding structures. So this is known as a polycode in which the interpretation of each symbol sequence is always the same and does not depend, all right, on the value of the preceding symbol. So basically over here, now this is going to be a code which will appear, okay. Digit value depends on the chosen alphabet code. So let's just say now the first box here will indicate material. So let's say I say M5. So M1 could mean polypropylene, M2 could mean ABS, M3 could mean, mixed polypropylene with a certain percentage of pigment, for instance, M4. So as soon as I see M5, then I will know what it is and I know what to take. The form of the material, okay, whether it is in, granules, whether it's in pellets, all right? So this probably will be MF, let's say 3, for instance. Material property, and then the bending method, of course, if you're dealing with bending, all right, the type of tolerance present, okay. So in machining, all right, what is the level, okay, whether it's a tight loose fit, all right, interference fit, okay, and then the testing method once it comes. So all these things will reads the code, they will know what to do. You and I will not know what to do because we are not in the production environment. So once you're in the production environment, the GT code is set. So all we need to do is just look at the code and select all the processes. So here we have our engineering drawing, okay? And from that, we will form the GT code, okay? And this GT code becomes your process plan. So it says process plan retrieve or process plan edit, okay? Of course, if it's the first GT code, then that's going to be the first GT code. Otherwise, all right, you retrieve from your previous plan, you edit it to suit your requirement of this new product, okay? And where do you retrieve this? You retrieve this from the master plan. So this is like a file system with loads and loads of different process plans already made. And then you get your new process plan. Once you finish your manufacturing, this process plan, all right, will be, okay, fed back. Pointer, okay. Okay, so once this is done, the process plan will be fed back into your master plan. Okay, so this is the variant approach. Now we look at the generative approach. Okay, so this is a process plan created from scratch for each component without human involvement. These systems are designed to automatically synthesize process information to develop process plan from a part. All right. Okay. So it does require or store predefined master plan. Okay. Basically, the concept of a generative approach compared to the variant approach is easier. It uses the idea from the variant approach, but it is custom made or tailor made for each new products. Okay. So it is in this generative approach that the concept of CAPP becomes prevalent. So if you would have paid attention to the explanation earlier on, the variant approach is more of a manual production system. The generative approach is more for a computerized production system. So therefore, you have your part drawing. It's already in CAD. You analyze the process in CAM. You generate the code and you directly come in. So there's no necessity to actually really have a predefined master plan. The only necessity here is when you're a planner or a technician or anything like that, when we are doing the analysis, we don't rely on this, but generally it does help us with an idea of how to move forward. Okay. This contains the logic to use manufacturing database and suitable part description schemes to generate process plans. Okay. Process plans are generated by means of decision logic, formulas, technology, algorithm, and geometry-based data. So the link between the CAD system and the CAM system, okay, this is done through high programming sequence, okay? So a lot of decision logic is present. Most of the contemporary CAD systems being developed applies the generative approach. And this generative approach eliminates the disadvantage of the variant approach. So basically, it bridges the gap between the CAD and the CAM. So implementing a generative CAD system requires far more effort because this involves the codification of the various knowledge related to the manufacturing resources of the enterprise and building the algorithms to identify. Okay, so but once it is done, then it's highly automated. Okay, so it's a full automatic up-to-date process, okay, and you can generate each time a part is ordered, as I said, because it is done from a computerized point of view. Disadvantage, it requires major revision in decision logic if your equipment that you're going to actually channel to is changed or a new equipment is acquired. So same thing, you have your part description, your drawing, and then you have your process plan logic. Okay, and how your process plan logic is made is from your manufacturing information again. But this is the process plan logic is now in the CAM environment. So from the CAM environment, all right, let's just say now you're going to simulate a drilling motion in CAM. So, of course, CAM being CAM, I can just have, let's just say, let me try the pointer again. Okay, I'm so sorry. The pointer option is not working for me today. I'm not even sure if it's an internet issue. Escape and try. Okay, so let's say I have a block, all right, and I'm going to drill a hole. So if I'm going to drill a hole, okay, I'm so sorry, I can't do anything. So you just have to imagine, all right? So if I have a block and I'm going to drill a hole, all right, and I want to know which tool to use. So if it's CAM, you can just simply select one tool after another, okay? But that's not the purpose of CAM. It's not for us to play, right? It is for us to understand which is the tool needed for that kind of particular hole. And where do we get that information from? From the machine tool manual, okay? The type of, from the cutting tool manual, all right? The type of machine tool, okay? What kind of tools are going to be used? And in holding the product, what type of jigs, what kind of material can actually tolerate this kind of tool tips and all those kind of things will be from the information that you have. Okay. So the application of your cam itself comes from the information. Otherwise, we will not know which to select. Sometimes which what we call which attributes or which constraints do we put in our cam software. So it is not a completely blind process. The cam itself, you must know how to run it. Okay. If you're going to do injection molding, you must know that you need to place a gate over here and all those things. Okay. And once it is done, then the process plan is generated. So what I'm trying to say over here, it is software based, all right, compared to the variant approach. So now the implementation techniques of CAP, especially in the generative aspect. Okay. Just give me a minute. All right. It uses logical decision. All right. The simplest approach is to code the process capability in a computer program. So of course your softwares are all coded, right? Naturally, hence we can run the application easily. So the methods used, all right, for classification of this coding is divided into three: decision table, decision tree, and AI. Okay. So basically, I'm going to skip the explanation and go to a decision table. So assuming now, okay, you have even the variant approach, all right, can use this, okay, which is applicable for the manual production as well. So in your particular machining, let's say you're going to drill, all right. So in drilling, we need to look at condition 1 and condition 2. Let's say condition 1 is lubrication, condition 2 is reliant on the two types of speed, for instance. So if you say, all right, condition 1 is the speed, condition 2 is the lubrication. So if your speed is, let's say, the RPM is a certain RPM, let's say 5, all right, let's say 20, and then so the lubrication is on. If the speed is 5, lubrication not on, all right. So, and then we move on to the next condition, all right. If it goes into some other speed, and then, okay, do we on the lubrication? And then both, all right, no spindle speed, no lubrication, for instance. So this will lead into us forming our actions. So if you have been given an exposure, right, to computer programming, this is how we create our program lines. Different loopings are created based on this yes and no logic. Okay. So as I said, this can be manually used, and this can be used to program a code. Okay. So this decision table can also be represented in the decision tree format. So we have the yes and no, the same condition, all right, and applicable here. So action A, action B, action C, action D. Okay. Now the third aspect is the artificial intelligence. Okay. So what is artificial intelligence over here, right? Basically, can you all explain to me what do you understand by AI?
Artificial intelligence robot.
Okay.
Genius robot.
What robot?
Robot with a mind.
Robot with a?
Yeah, okay.
Sorry, not clear. Can you please repeat?
Is it a set of instructions on a machinery?
Okay, set of instructions on a machinery. And then for someone who said robot, I think you all added some things. Afnan, what did you say?
Robot with instruction.
Robot with instructions. What else?
Self-programmable.
Okay, self-programmable. Okay. Any other
A simple artificial brain?
simple artificial
Brain
brain?
for
Okay.
the machinery.
Okay. So now the term itself says artificial intelligence, right? Now, of course, intelligence is very much attributed to humans, okay, because it's a thinking process. So when we call it artificial intelligence, because we are making non-animate objects to function like as if they have their own thinking process. Okay, so the robot moves, functions by itself. All right, and how is this happening? Okay, so how is this happening is basically we are incorporating as many sensory perceptions as we can, which is closely linked to nature and life. All right, so basically, let's say we have a robot which is supposed to do a pick and place, all right, in a production line. So it's supposed to detect any errant products. Okay, so what will happen over here is the robot will look at, let's just say, products which come out with an extra heat. Okay, how is the robot going to understand that? So you have to attach a sensor to the robotic arm. Okay, a heat sensor, and the heat sensor has to be programmed with a certain range. So if the part that comes out falls into the range of error detection, then the robot will not pick it. Otherwise, it will pick and place. So that's a very basic example I'm giving. So we have moved further into AI, right, in so many other aspects, which you have seen. One which is most common, wait, if I could. Right. Wait, I wanted to show you all this video on machine vision. Okay. So
Thousands of companies
watch
across
this,
the globe produce and transport millions of products each day. Many of these products would not be possible without machine vision to help guide, inspect, gauge, and identify their products. Cognex's vision sensors and 2D and 3D vision systems are all powered by advanced algorithms and robust technologies like PatMax for object location, image formation, 3D vision and measurement, barcode reading, OCR, advanced color tools, and deep learning tools. These industry-leading solutions solve simple to highly complex applications, like pick-and-place robotic guidance, validating dimensions of auto parts, ensuring caps are sealed on detergent bottles, and verifying characters printed on food packaging. Cognex vision systems are built with the manufacturers of today and tomorrow in mind. Rugged housings deliver top performance, even in harsh industrial environments. Modularity offers field customizable solutions for your specific applications. And intuitive software enables fast and easy setup and deployment. With industry-leading technology and world-class application support, you can rely on Cognex machine vision solutions to help optimize quality, maximize throughput, and minimize waste. For more information, visit Cognex.
Okay, so that was an example, all right, of usage of artificial intelligence. Basically, this is machine vision, all right, is something which is really picking up in the IR 4.0, Industry Revolution 4.0 concept. Okay, it deals with smart manufacturing, smart machining, smart factory, and all those kind of things. Okay, so here, as you yourself saw in the video, there is a very highly sensitive programmable code, okay, which allows the machine to be able to detect functions manually humans do. Okay, how it is done, it's highly incorporated with different types of sensors, okay, linked to the machinery. So this is the concept of AI. So basically, in the generative approach, all right, AI is able to perform build the manufacturing sequence, all right, custom made, okay, due to its qualitative, subjective, all right, imprecise and company specific nature. So according to what you can see now, you can make all these changes, all right. It's also designed to cope with knowledge characteristics. So it's much easier to modify than custom fixed logic, okay, in conventional system, all right. because the knowledge in expert systems is clearly represented and separated from the planning of the mechanism. Basically, you are now using CATIA, but you simply have no idea what is the program behind CATIA. So you are using your manipulating, you are applying CATIA, all right? And you do not have to worry about the mechanism behind it, okay? So this is a frequently used method in the generative approach, okay? So this is a summary of how a variant cap system, all right, will work. You have your part drawing. Then this coding is what we call the group technology coding, which I mentioned just now. You have your process plan. Everything is brought into your new plan. Okay, and then you get your final plan, which is later on fitted back into your collection of your baseline plan. In the generative approach, you have your user with your part drawing. You have your interface engine, which is your software system. And how to operate the software system, you need to have your entire, in this case, we are talking about manufacturing, knowledge base. So you have your process parameters, the cutting tools, the machine tools, selection rules, all this is your knowledge base, okay, which you use to support and operate your software, okay. Now, the hybrid approach is, of course, as I mentioned earlier, it is a combination of both. In general, we use, if you look at the generative approach, okay, aspects of variance approach is used over here. So what is variant approach aspect? The variant approach aspect actually highly forces the user to understand the manufacturing knowledge. So okay, I'm going to compare myself now to the lab technicians, all right? So my knowledge of manipulating and operating the machines, let's just say in FKM, is far lower than the technicians over there. Why? I teach the theory. I know what an injection molding machine can do. I know how it's operated. I can use CAM. But you ask me to go and switch on, manipulate, operate the machine, and suddenly troubleshoot when something goes wrong, and I will completely fall flat. Because I am not dealing with the day-to-day production, neither am I studying the evolvement of the machine, okay? So this is usually done in the variant approach by the low-level planners, okay, where they run the production facility, okay? Now that knowledge is needed in order to operate. So as a lecturer, I can very theoretically operate my software. But if as a lecturer, I have the equal amount of knowledge the technician does, then you can imagine when I operate my software, all these things will be far better. Now, as a student itself, you can operate the software. But how you will do it? You will do it on a test and try basis. Okay, let's put this now, what happens? Let's try that temperature now, what happens? Like that, okay? So I have the theoretical knowledge and the technicians have the hands-on knowledge. For polypropylene, they have tested, this is the range of the injection, a melting temperature. So they will know how to advise, okay? So in the hybrid approach, we use the variant as well as the generative approach. So the variant approach aspect is the knowledge. The generative approach aspect is the ability to bridge the CAD and CAM software, okay? Leading into a hybrid approach. Okay, so these approaches, they are actually shared in this chapter for us to understand or maybe appreciate how it works in the production plant. Okay, so now moving into what exactly happens in a manufacturing system. So when you have a CAP system, all right, we need, like early on, I said we need your geometry, part design, we need the manufacturing facilities, we need the manufacturing capabilities. So your part design, PDIR, part design internal representation. And then you have your manufacturing resource internal representation and your process plan internal representation. So this is your capability facilities and this is your capabilities. Okay, now we come into SIM. All right. So what is SIM? Computer Integrated Manufacturing. Okay. So we have talked about bridging CAD, bridging CAM, everything is now all seamless, integrated. So now what's that integration all about? All right. Now the definition given by the Society of Manufacturing Engineers is, it's an integration of total manufacturing enterprise through the use of integrated systems and data communication. All right. Just give me a minute. Just a minute. Okay, apologies. All right. Okay, let me come back. All right, so it's defined by SME. All right, it's the integration of total manufacturing enterprise through the use of integrated systems and data communications, coupled with new managerial philosophies that improve organizational and personal efficiency. So SIM is going to work with the addition of the managerial philosophies. Okay, so we have talked about the technical aspect of CAD, CAM, and everything, and none of this is going to be successful if you don't have some philosophy which is going to improve the functions in your organization. So like I mentioned earlier on in the first part of the chapter, when we're looking at the QFD, right? Quality functional deployment, all right? It talks about how we use the voice of the customers to actually form the product, and the voice of the customers is kept intact throughout the product development, okay? So when I mentioned that, Toyota is very popular for using this, all right? They have a lot of all these managerial philosophies like Kaizen, Six Sigma, all right? And all these things, okay? So these things are used just in time. They're used, all right, to improve the organization and on a personal, efficient note, okay? So basically, it involves integration of all the functions in an enterprise. So in chapter 1, I showed you a slide on how SIM functions, a complete integration of all the department, basically, okay? So again, when we look at SIM, you can see now your customer being the center of the attention. So the customer being the center of the attention, which means will bring to the model-based engineering. So we saw that in chapter 1 as well. The model will be the center of attention. So there will be teamwork. The organization has to step in, and these other people in the organization, okay, they share the knowledge and they use the system, and all the different departments will ensure the success of the product, okay? So there are 6 areas in this manufacturing enterprise wheel, all right? Success depends on the customer, okay? So when we talk about the customer, because we need a customer, we need a problem, then only we can solve the problem and make a design and manufacture it. Then we need to deal with the organizational structure of the enterprise. So an organizational structure has to be very carefully made, and it cannot be, something where it's lost, okay? Everyone in the organization must be holding a responsibility, and the structure has to be very systematically formed, okay? So the work breakdown structure has to be well done, and then you will see the organizational structure. And then knowledge has to be shared across the organization, both the experience as well as the database itself. The systems that are involved and used in the total enterprise has to be up to mark, current, contemporary. The resources and the responsibilities of the enterprise has to be made such it's a ownership by each and everyone working in the enterprise, okay? And all this will only work when you have the infrastructure to support your manufacturing plan or process. Okay, the next few slides are basically just information for you all right? So it functions in CIM, all right? A specific area on production. So you have your business system, you have your CAD, CAM, and then you have your production activity, and it's just a byproduct of the production activities like the tool preparation. So, okay. And then we have the CIM implementation, which is described in the hierarchy level, all right? From the equipment to the factory level, what happens? So from the equipment, all right, we go to the workstation. There will be a few people in the workstation dealing with the equipment. And from the workstation itself, there will be a few people in the cell monitoring the workstation and the equipment. From the cell, it will lead into the system, all right? Okay, and then directly to the factory. So the major functions in SIM, as in the box, All right, design and engineering, the master planning for the production, the process planning, quality assurance, and your sales. So some interface requirement which is needed in SIM, all right, all this for manufacturing purposes, okay? Sorry. The machine tools, fixtures, method, the quality assurance. So these are all some interfaces for you to just understand further, right? And we come to the final slide, all right? The benefits of SIM itself. It improves operational control because it deals with the managerial capacity. So basically it deals with how we're going to organize and run the structure and the production. Improves short-run responsiveness, which consists of engineering changes, processing changes, machine downtime, okay? If you don't have an operator available, right, through SIM, we usually can sustain, okay? Tool failure, late material delivery, because we have concepts like just in time, we can avoid these things, all right? And in the long run, it also accommodates changes, all right, to product volumes, product additions and introductions, different parts, okay? And this will lead to reduction of inventory as well as increase of the machine utilization. Okay. So now we are done with chapter 3. Any questions so far? Is everyone okay?
Yes, okay.
So far okay? No questions?
Okay.
All right.
Okay.